Energy discretization, as discussed in Part B of this lecture, provides ample opportunities to engineer materials on the nanoscale with unique electronic properties. Furthermore, with the unique control over material synthesis on the nanoscale, utilizing thermodynamic fluctuation principles, as discussed in Part C, the range of manufacturing opportunities is even further widened. Nanotechnology provides to date the possibility of designing ultra-small uniform structures with tailored and unique opportunities, heterostructures of simple to complex architecture, and nanocomposites that capitalize from multiple preferential material aspects. Thereby products originating from nanotechnology can be either small or scaled up. In this closing chapter of this introductory course, I will show some examples of nanotechnology-based applications, devices, and tools. There are many routes of making nanomaterials. We distinguish between two main classes, the bottom-up approach and the top-down approach. Pyrolysis, a decomposition process at elevated temperature, is an example of a bottom-up approach. It provides the opportunity to synthesize nanoscale heterostructures with targeted local heterogeneities and unique shapes, besides others. Illustrated here are porous structures, hollow spheres, and ball-in-ball spheres utilizing different inorganic materials. Another bottom-up approach is self-assembly, utilizing organic materials. Spontaneous molecular aggregation in a medium of appropriate components provides vast opportunities to design macromolecular structures of highest complexity and functionality. One of the most widely used top-down approaches is lithography, typically involving an etching source such as light, a sensitive material, and a mask. The example here, a 2-photon laser, produced a three-dimensional replica of a car with nanometer detailed structure in just a few minutes. With increased control and speed over processes and the implementation of nanomaterials and structures into macroscopic systems, that is, being able to scale nanoproperties up, nanoscience has matured into a valuable technology. It affects fields from optics, electronics to coatings, with a vast variety of property enhancements and modifications as listed here. For instance, nanotechnological approaches towards catalysis brought forward new materials of higher reactivity, making processes more cost-effective and environmentally friendlier. In drug delivery, nanoscopic vessels could be designed that carry more targeted smaller loads to the sites in the body where they are needed. Nanotechnology also impacted former device and operation technologies and brought them down to the nanoscale. Two examples are provided here. Sophisticated mixing of multi-component systems are in need of additional constraints that go beyond thermodynamics. In this particular example, the nanoscale utilizes the unique fluid flow fields on the nanoscale in which turbulences are kept in check. Another example are electromechanical systems, short EMS. There are many EMS applications, as for instance gyrosensors found in portable electronic devices and in car airbags. By bringing EMS to the nanoscale, many other opportunities open up, such as here depicted with a high-density recording system, not much different from the classical punch card, just much faster, with a recording density in the terabit regime. While originally just a scale, a thousandth of a micrometer, an academic curiosity that has assisted scientists to analyze and visualize microscopically material surfaces and explore the mesoscale between the atom and the bulk material, the nanoscale grew to a very powerful technology at the dawn of the 21st century. Some scientists believe that this field is with us since colloidal sciences over a decade ago. Be that as it may, as a mainstream technology came to us much later. It had first to be seen to be believed. In my view, it started with the invention of the scanning tunneling microscope by Pinnick and Rohrer that has provided a simple and direct visualization tool of the nanoscale. With this, we reach the end of this short course of what makes Nano tick. Having first provided some historical background, I try to introduce to you nanotechnology from two angles that are strongly intertwined. One, the quantum nature that affects the electronic structure of materials and defines the interaction fields and properties of materials, and two, the atomic molecular stochastic nature of condensed matter that provides the framework for processes that bring materials into existence. We finished the discussion with a few glimpses into applications and tools. I encourage you to work through the questions in each section and revisit the slides that are provided in separate PDF files. Please also note there is a wealth of information available on the web. Thank you for your attention.